For our fluid mechanical dissection, we had a weed whacker.
The whole system runs off a one-cylinder engine. This engine is a two-stroke, and in order to start it, you need to pull this string manually. When you pull this string, what it does is brings gas into the top of the cylinder, and the spark plugs ignites this fuel-air mixture, which starts the cycle. This system runs off a two-stroke engine. The first stroke takes in air and fuel mixture from the carburetor and ignites it. The explosion in the power stroke results in the downward force on the piston, which drives the system, and the excess waste products from the combustion are exported out into the exhaust.
So this is a video of the throttle in the carburetor opening and closing, and inside of that there's a venturi, which is a converging diverging region that generates low pressure at the throat for the fuel and air to combine. So when the throttle is open, the pressure downstream the venturi is about 1/3 of the atmospheric pressure, and the engine is running at maximum power. But when the throttle is closed, the pressure in the carburetor is about atmospheric, and it gets very little fuel, so the engine is running at minimum power. Here are our drawings of the venturi. So we can see that the diameter of the throat is way smaller than the diameters at the inlet and outlet, and these are the streamlines that we estimated. And we can see that the pressure at the throat is less than the atmospheric pressure, and the speed at the throat is greater than the inlet speed.
Because of what we know about the venturi, along with what we observed during the dissection, we made specific assumptions and simplifications in order to analyze the system and make calculations. The first assumption that we made was to use incompressible flow analysis. This because the speed of the flow isn't high enough to vary the density throughout the system. Also, using the dimensions that we found, we were able to calculate the Mach number at the throat, which was roughly 0.126. And because this Mach number is less than 0.3, we can say that incompressible flow is a valid assumption. We also felt that it was safe to assume that the pressure entering the system at the inlet is atmospheric, which allows us to solve for the unknown values at the throat. And our last main assumption was that all flow is inviscid. This is because of the high Reynolds number that we were able to calculate, as the Reynolds number determines the properties of an incompressible flow, and it tells us whether viscous effects can be neglected. And so based on our calculations, we found that our Reynolds numbers were high, and we know that because the fluid mixture is zooming through the tube over a short period of time, viscous effects can't diffuse too far from the surface. And also because the fluid mixture in this case is predominantly air, the viscous effects are easy to neglect in comparison to using a more viscous fluid.
The incompressible flow assumption allows us to cancel the densities on either side of the conservation of mass equation for quasi-1D flow, while the inviscid flow approximation allows us to simplify the Bernoulli equation, in which we also neglect changes in the gravitational potential energy due to the small scale of the system. Using the conservation of mass equation, we can find an expression for the velocity at the throat, which we then use in the Bernoulli equation to find the pressure drop as a function of the intake velocity. We then shift our focus to the fuel tank, where we can use a streamline to connect fluid at the air-fuel interface, where the pressure is atmospheric, to fluid in the fuel line. This allows us to again use the simplified Bernoulli equation with the same pressure drop to calculate the fuel velocity in the line. Using our measurements for the cross-sectional areas of the intake in the fuel line, we can convert the velocities into volumetric flow rates to find an expression which shows that the flow rate of fuel is linearly proportional to the flow rate of air, resulting in a mixture with a fuel-to-air ratio that is independent of the rate of airflow and thus of the engine RPM.
Thank you.